Yeah, hello Ravindra. So we will wait for 3 minutes more and then I will start. Okay, so hello everyone. So I will introduce myself a little bit. So I am Anjali Neki. I am a PhD student in IIT Kanpur. So I'm pursuing my PhD in physical chemistry as a theoretical and computational chemist. So today I will be solving mostly 2015 GATE question. So yes, I will share my screen now. discuss some basic. Now, the defects in solid are any irregularity in the pattern of crystal arrangements in solid, and this is called imperfection in solid or defects in solid. The crystal defect occurs as point, along line, or in the form of a surface, and they have been classified as point defect and line defects. So we are focusing on point defect. So the point defect are the imperfection in the crystal that is due to the dislocation of a particle from one position to another position in the lattice. So this is for our understanding. So the types of point defect can be classified into stoichiometric defect, non-stoichiometric, and one impurity defect. So our main focus is on stoichiometric defect. So this defect it is also called intrinsic defect or a thermodynamic defect. Because in stoichiometric defect, the proportion of the elements in the solid is not disturbed. So this defect arises when there is some vacancy in the crystal lattice, or when some constituent particle move from their original site and occupy the interstitial sites. So the stoichiometric defect have been observed both, as you can see, in non-ionic solid and in ionic solid. Okay. So again, this stoichiometric defect in ionic solid, it is classified in two different defects, which is one Schottky, other one is Frankel defect. So to simply understand this, so in Schottky defect, it is the defect in the crystal is observed when, so you can see this is a representation of lattice. Okay, so this is a two-dimensional lattice where my cation are present in orange dots and my anions in negative blue. Okay, so this is the arrangement in two-dimensional lattice of a ionic solid. So if I go through this demonstration, so to understand Schottky defect, this defect is also known as the point defect. And why is so? Because we observe when an equal number of cation and anion means both are missing from the lattice point. Okay, so the presence of the Schottky defect does not change the stoichiometry of the crystal. This has to be noted because at the same time the ratio of cation and anion is being neutral, so it is not affecting the stoichiometry of the crystal, but what it will affect? It will affect the density of the overall crystal. Okay, so the presence of this defect lowers the density of the solid. So if this is my crystal, so after the defect, say this and this one cation and one anion is missing from the lattice point. Okay, so overall the density of the lattice will decrease. Okay, now to understand the Frankel defect, so Frankel is again simply in any crystal when ion leaves its regular site. Okay, when ion leaves its regular site and occupy an interstitial site here, it is now the ion is not leaving the whole crystal, but it is occupying the interstitial site. So this defect is termed as the Frankel defect. The only difference between Frankel and Schottky is that the density of the density in the Frankel defect, it remains constant, as my anion or my ion are actually not leaving the whole crystal, but the small size say cation will move to the interstitial site, okay, or space. So this defect will look like, say this cation has moved and moved to say anywhere in between here, okay, or here, okay. So this is the Frankel defect. So simply, you can see the example for Schottky defect are NaCl or KCl, and in Frankel defect it is AgCl or AgBr. Again, the point to be noted here that in Frankel defect, the size of the cation should be much smaller than anion. Usually it is smaller, but if it is smaller than the anion, then we can say that that the Frankel defect may be observed, because it will be easy for the cation to move towards the interstitial space or void. Okay. So this defect lowers the density of the solid, as I have discussed. Due to this defect, the atoms or ions can move within the crystal lattice. Correct? Due to this defect, the atoms or ion can move within the crystal lattice. Again, it does not affect the density of the solid. So these are the two differences. Now coming back to our question, which was asked that one of the following statement is incorrect. So option number A, the Frankel defect is a cation vacancy, which is correct, because cation is vacated from its lattice point and a cation interstitial, correct. Frankel defect is an anion vacancy. It's totally not correct, because anion has a larger size, and we have discussed it in Frankel. Only cation of smaller size in comparison to anion move towards the interstitial side, and a cation interstitial. It is wrong. Okay. The density of a solid remains unchanged in case of Frankel defect. This is correct. Density of solid decreases in a case of Schottky defect. This is also correct. So the incorrect option is B. Okay. I will highly recommend you to go through NPTEL reference Lattice Imperfections and Crystal by Professor Madhav Ranganathan, Department of Chemistry, IIT Kanpur. The link is given below. Thank you.
Yeah, Navreet Kaur, if you have any doubt, you can ask. Okay, then I will move to the next question.
In this video, I will be solving GATE 2016 Chemistry question number 49. This question states that the temperature composition phase diagram of the two component system made of X and Y is given below. At a temperature of 288 Kelvin and starting at a point P, Y is added until the composition reaches S. Which of the following statement is not true? So before we move towards the conclusion or the answer of the statement which is not true, let's get into some basics. So the phase diagram or equilibrium diagram is a diagram in the space of relevant thermodynamic variables, example temperature and composition, or pressure and composition, indicating phases in equilibrium. This is called as phase diagram. Now the phase diagram of two component system can be in liquid-liquid phase, in liquid vapor phase, in liquid solid phase, or in gas solid phase. Now in a given problem we are discussing the liquid and solid phase of the two component system. So yes, so the axis for the two component system, the temperature axis. So if this is the temperature axis and this is my component in my problem, I will discuss this in a similar manner. So this is say component P, and the another is S. Okay. So this is again the temperature axis. Now there will be some one point in the temperature axis where it will be a melting point for my component P, above which it will be a liquid and below which it will be a solid. So if I join these two temperature axes of the component P and S in this manner horizontally, then this will be known as the composition axis. Now the composition axis is such that it start from 0 and it goes to 100. That is, 0 means it is pure P and 100 means it is pure S. Now in between it will be 50-50. So it will be 50% of component P and 50% of component S. Now we can denote the composition axis as weight percentage, okay, from 0 to 100. For a given problem, so we are actually given with I will just draw it here. So this is the separation line for solid X plus Y. So actually, yeah, so I have been given component X and component Y, and P and S are the 2 points. So yes. And now here it is given that it is pure liquid. So if I am talking about a point, say, so this is P, this is Q, this is R, and this is S, okay? Yes. Now this is 288 Kelvin, it is given. So actually we were given with a mole fraction of Y, okay? So we can either denote it with the weight percentage or mole fraction. So just we will discuss the fundamental here. So at point Q, if you look at point Q, what you will find? You will find that it is placed with a composition of liquid of X and Y both. So it is the system where my system is in all liquid phase. Okay. So I will just write it X and Y in liquid phase. And as it was given in the question that the starting point is say P and then Y is added until the composition reaches S. So if my starting point is P, also my P belongs in between of a solid and a liquid region. So this particular region is actually not pure solid or pure liquid. So it will be at P. So my X is the starting here. So it will be more of X, correct? And my Y is adding up. So we can say that it is in a solid plus liquid region. Okay. Now, because it is not specifically on the axis, so I cannot say it's a pure X or not a pure X. So I will not talk about the composition of X and Y here, but it is the solid and liquid are present in almost equal proportion, we can say, because it is almost at equal distance from both the separation lines. Okay. Also, yeah, let's move into another point. At R, so R is the point that is lying exactly on the line which is the separation or the equilibrium line between liquid
okay, and solid. So this is at equilibrium between, not exactly solid, but yeah, equilibrium between liquid and liquid plus solid phase, okay. Now the last point, that is at R, at S. So this is the, again similar like P, so it will be the system which is having solid plus liquid phases together, solid plus liquid phase. So I can, in the given problem, we are actually given with the option that at S, the system has more solid than liquid. But yeah, maybe it is true. So we cannot specifically say, but yeah, more solid than liquid, but it is in a liquid and solid phase. Now let's move into a problem. So at P, the solid and liquid are present in almost equal proportion. Yes. At Q, the system is in all liquid. Absolutely correct. At S, the system has more solid than liquid. Yeah, I mean, it seems like, but it's not specifically. So we'll give it maybe. At R, the liquid is pure X. Now, it is talking about at R. So at R, there should be one equilibrium established between the liquid phase and the liquid plus solid phase. So it is saying that it is pure X, liquid in pure X. Now, first of all, it is not even pure X here, because if we go through the composition axis, then it will be mixture of X and Y, which is more of Y here. Okay. So this statement is totally incorrect, because it is not pure X and also it is not liquid. So it is a mixed equilibrium established between when the point is in the line. So that is it will be the equilibrium established between the liquid phase and the liquid plus solid phase as given here. So the option D is incorrect. And I will highly recommend you to go through NPTEL reference, Phase Diagram Introduction by Professor Rajesh Prasad, Department of Applied Mechanics, IIT Delhi. The link is given below. Thank you.
Yes, so any doubt, Navreet or Narmada?
Yes, ma'am.
Yeah, if you have any doubt, you can ask or.
Okay.
Okay, so I will move forward and share another question.
Hello everyone. In this video I will be solving GATE 2015 Chemistry question number 46. This question states that the distance between two successive planes in a simple cubic lattice with lattice parameter A is. We are given with 4 options. So before starting, let's discuss some basics. So the mathematical description of a plane and a normal vector and a normal vector. So for example, if you look on your right, so this is x, y and z axis, and here if the intercept of a plane that is shown in blue color is a, b and c respectively, then this plane has an equation as shown here, x by a plus y by b plus z by c equal to 1. Okay, and in a case where any of these three intercept, that is A, B and C, these are any of these is equal to infinity. For example, if the intercept A is equal to infinity, that means that the plane never intersect the x-axis, okay? And then the equation will become y by b plus z by c equal to 1. This is the equation of the given plane. Now, if A, B both become infinity, then the equation of the plane is just z by c equal to 1, or we can write it as z equal to c. So this particular plane I have shown here in red. So this is the only intercept with the z-axis of this plane, and so this is the plane. Also, for every plane, there is a unique normal vector for every plane. For example, in the plane in blue, this plane has a one unique normal vector that is shown in and having a direction, that is n vector. And also for this plane in red, we have vector in k direction, that is here because if you this is the equation of the normal vector, that is n vector is proportional to I unit vector upon A plus j unit vector upon B plus k unit vector upon C. So this is the equation of the normal for each plane. Okay, so if this normal is for, I am describing it for the plane which has only intercept at z direction, then A and B become infinite, that is this and this portion becomes 0. So only k by c will remain. So that is why it's in the direction of having a direction k unit vector. Okay. Now the unit length, when we find the when we remove this proportionality and we find the unit length, so so it get the whole equation of the normal vector get divided by the length of the vector. So this is how we find the unit length. So this will become 1 upon a square plus 1 upon b square plus 1 upon c square in a square root will divide the equation of the normal vector. Now coming to the concept of parallel lattice planes. So if you assume here, this is a one-dimensional lattice point arranged in a lattice. So this is a one-dimensional lattice plane. Okay. Now if this is the axis in blue, okay, say A and B, and again in red, say again A and B. So in blue, if we see that there is a plane passing through these two atoms, okay. So these two atoms, so blue plane passes through them. So it will cut the axis in A and B in some point. And again, if there is a similar plane parallel to it, passing through another two atoms in a similar manner, such that these two planes are parallel to each other. Here actually the lines are not straight, so but assume they are straight planes and they are parallel to each other. So then we get a series of parallel planes, and these are called the family of parallel planes. And we have a special notation for these parallel planes. We call it as Miller indices. Okay, so this is what we have. Now coming to the concept of Miller indices for lattice planes. So assume that lattice translational vector, that is the A, B and C vector, are perpendicular to each other. For example, in this figure, you can see that A, B and C are perpendicular to each other. So the first step is to look for lattice plane closest to origin, and that plane should not be passing through origin. If it is, then we can take another successive plane which is parallel to it. For example, here this is the plane in blue shaded in green. So this plane intercept axis A. Okay, you can extend it axis A, axis B, and axis C such that it intercepted in 1, 3, 2. Okay, so if I write intercept at A first, that will be A, 2, 1. Okay, so this is the intercept for the A, B and C vector. Okay, now the next step is to take the reciprocal and multiply by the least common multiple. So we will take the reciprocal of each intercept and multiply by the common multiple. That is, here it is 6. So we'll multiply it by 6. So the Miller indices, it is the notation is such that it is notated in square brackets. So it is 2, 3, 6 in square bracket. So this is the Miller index of that particular plane. So now the case is if the intercept is negative, so use bar, for example, -2 can be written as 2 bar, okay. Now the Miller indices for the direction, so in square bracket, I can just denote for making it simplify and generalize HKL as 2, 3, 6 here is HKL, okay. So this in square bracket gives me the direction, and if it is in normal bracket, then it will be a plane or a surface. Then in square bracket for 2, 3, 6, this is the actual direction, that is the 2a vector, 3b vectors plus 6c vector, okay, under root divided by the length of the given plane or vector. So it will be 2 square plus 3 square plus 6 square, okay, taking the square root. Now coming to the cubic system. So if I have moved from one dimensional lattice plane to a cubic system, which is 3D. So here we have again same type of arrangement, 3 axis A, B and C, and these are the lattice point in 3-dimensional. I tried to make it. Then in our question we were asked about the distance between two successive planes. So there are two planes, so both have the same direction or plane or surface, that is 110, 110 in a simple cubic lattice with lattice parameter A. So the lattice parameter is A, and I have only shown for example 1101 plane here. There will be another plane successive to it, that is parallel to it. So yes, to find the distance between these two planes, we need to apply this formula, that is the distance between two planes DHKL is equal to A is my lattice parameter divided by h square plus k square plus L square, that is my Miller indices. Now my D110, this distance between these two planes will become A upon under the root 1 square plus 1 square, that is root 2. So the distance between two successive plane 110 in a simple cubic lattice is equal to A upon under the root square root 2. Okay. So the correct option for this question, the distance between two successive plane in a simple cubic lattice with lattice parameter A, is option number D, A upon under the root 2. I will highly recommend you to go through the NPTEL reference, Miller Planes, Miller Indices by Professor Madhav Ranganathan, Department of Chemistry, IIT Kanpur. I am attaching the link below. Thank you.
Yes, so was it clear? You have any doubt?
No.
Yes, Narmada. Okay, it's clear. Narmada, you had any doubt or? Okay. So I will be moving to the last one. Okay.
Hello everyone. In this video, I will be solving the 2015 chemistry question number 25. This question states that the electrical conductivity of a metal, we are given with 4 different options. Before moving to the given option, let's move into some basic. So, the metal is actually denoted or demonstrated as or studied as the electron C model. This model here, cation or anion is actually denoted as positive species here in this color, and the free electron is in surface or is free to move. That is why we can say that the positive atomic nuclei is surrounded by a sea of delocalized electrons. Okay, so this is there, and then so how what is the electrical conductivity of metal? So the electrical conductivity of metal, I will at the end of this video I will give you the reference where you can actually get some insight into the band theory of solids. So in band theory of solid, you will get to know that there is a Bloch's theorem which is used to develop the band gaps between the in a metal or semiconductor or insulator, or when there is a perturbation. For example, any kind of perturbation like increase in temperature or some doping or etc. So how that the band, the energy band or the band gap before and after it, there is a gap is introduced, and that is why in we can see you can see that how the perturbation affect the conductivity. So that reference I will give you at the end, but here we can discuss that how temperature affect the electrical conductivity of metal. So when the temperature is increased, so when the temperature is increased, so what happened that the positive ion inside the metal conductor, the atoms basically, they start vibrating. The positive ions, or we can say nuclei, start vibrating, and the thermal speed of this electron will get increased also, correct? Because as temperature is increasing, the energy will vibrate the atoms, the positive ion or cations, or plus the thermal energy of the free electron will also get increased. Will get increased, okay? The result is such that it will instead of increasing the conductivity, but it will increase the resistance towards conductivity. How such? How it is happening? Because the free electron definitely have more thermal energy and more energy to move faster, but also because there is a vibration in my atoms or my ions or my nuclei, so there will be a increase in the resistance because of that, okay? Resulting in an increase in resistance. So therefore, a decrease in metal conductivity is seen. Okay. So the option that we were given is that electrical conductivity of metal increases with increasing temperature, that is false. Decreases with increasing temperature, this is correct. Is independent of temperature, it is saying that there will be no effect of temperature, but this is not the case. It shows oscillatory behavior with temperature. In the conductivity. So if we are talking about the conductivity, so conductivity doesn't show the oscillatory behavior, but it decreases with increase in temperature. Okay, so the correct option is B. So here is the NPTEL reference. I will recommend you to go through Band Theory of Solid by Professor Madhav Ranganathan. Okay, and Department of Chemistry, IIT Kanpur. The link is given below. Thank you.
Yes, so any doubt? Okay, so I have observed that both of you have joined my live session for the first time. So I will like to get to know you a little. So where are you from, Navreet Kaur? Okay, so you are pursuing your master's PhD. Okay, you have completed your master. So now you are preparing for PhD interviews and want to clear GATE. Nice. From where you have done polymer chemistry? Very nice. Okay. Oh, Narmada. Okay, wait. So Narmada has completed. So you are a male or female? I got confused with your voice.
What, ma'am?
I just got confused with your voice. You are male or female?
Female, ma'am, I'm female.
Okay. So you are doing your masters or have completed, Narmada?
Yes, I'm doing, ma'am.
Okay, nice. Okay, anything else apart from this you want to ask? Because I have to take your feedback also, and any input you want to give, or any other informal question you want to ask. Informal means regarding PhD and getting admissions and all.
How to do MSc project in IIT, ma'am?
Oh, it's I think if you want to go for a project student and join IIT for that, so you can actually, so your field is polymer chemistry, I can see. So you can search for the particular research project. So you can directly mail the professor, so that will be very helpful. Also, if there is always a project opening in every official site of every IIT. So if I will be talking about my IIT Kanpur, so there will be a project opening in their official site. You can go through that and apply directly, and you can also mention that you have applied and what are your credentials to the professor also. And yeah, that will be good. So you can actually check before applying that whether the project is apt for you or not.
Okay. Thank you.
Yeah. So Navreet, from where you have completed your masters? Okay, Punjab University. So you want to pursue PhD, that's why you are doing or PSC jobs.
Ma'am, if we qualify for GATE, whether we can do MTech in IIT, I am chemical engineering.
Yes, I think, because I know, because you have to check the eligibility criteria in the current stage, because previously I have seen that some of my friends and colleagues have done masters after doing their MSc. In masters, they have done their masters in chemical engineering in IIT. So, but you should always check the criteria, eligibility criteria now, because it might have changed.
Okay, thank you.
Okay, nice, Navrit. That's also good. So, if you don't have any other doubts and all, so you both can leave. Yeah, thank you so much. Any feedback if you want to give, it's welcome. Okay, thank you.